Welcome to the Deep Dive, the show where we cut through the noise, sift through the details, and bring you the core insights from a wealth of information.
That's the goal.
Today, we're taking a truly deep dive into 3D media, unlocking the realm of imagination. I mean, just think about how 3D technology has absolutely transformed our world.
Oh, absolutely.
You know, from the blockbuster movies we watch to the immersive worlds in video games, the precise blueprints in architecture, even the life-saving details we see in medical imaging. It's fundamentally changed how we create, visualize, and experience digital landscapes.
It really has. And for this deep dive, we've pulled together a rich stack of sources. We've got expert discussions on fundamental 3D techniques, detailed slides breaking down core concepts, and even a practical hands-on guide to SketchUp.
Our goal today is to really unpack this fascinating world for you. We'll pull out the absolute must-know insights so you get a quick but, solid grasp of just how powerful 3D design can be. But before we get too deep into the creative side, there's a surprising practical reality, isn't there? It sets professional 3D design apart right from the start.
Yeah.
The historically high barrier to entry.
Yeah, it's quite astonishing just how significant that barrier has been. For example, training a single professional 3D designer. If you factor in recruitment, training equipment, and the time it takes before they produce their first usable work, well, it can cost upwards of 5 million new Taiwan dollars.
Wow.
That's roughly, what, 160,000 US dollars? A truly significant investment.
5 million NTD for one designer before they even deliver their first project. That's quite an upfront cost.
It is.
And it's not just the training, right?
Yeah.
3D animation services themselves are equally expensive.
Exactly. We're talking at least 10,000 NTD per second for enterprise-level work.
Per second.
Per second. And for Hollywood productions, I mean, that could easily skyrocket to 200,000 or even 300,000 NTD per second.
Goodness. It makes you wonder if some companies just hire a single designer and, chain them to their desk. But seriously, what does that investment really buy them?
Well, this raises an important question, doesn't it? With AI advancing so rapidly in 3D, does it replace the need for human designers?
Yeah, that's the big question.
Our sources indicate that while AI is incredibly powerful and constantly improving, it primarily assists rather than fully replaces human designers, especially for highly customized and precise projects. The human touch and specific vision are still paramount.
So AI helps, but it doesn't do everything.
Got it.
But here's the really cool part, I think. Despite that high professional bar, the door to exploration is wide open for you, the listener.
That's right. Tools like Blender, which is completely free,
Totally free?
allow anyone to create professional-grade 3D work. So while the industrial costs are staggering, the opportunity for you to learn and create is more accessible than ever before.
Okay, so we've talked about the big picture and the sometimes eye-watering costs. Now, let's peel back the layers and get to the very first brushstroke of 3D artistry, bringing shapes to life, what we call modeling.
Modeling is truly the foundational stage of 3D design. It's where you create and manipulate three-dimensional objects.
Right.
And what's often overlooked in 3D modeling, despite all the advanced software, is that the true magic isn't just in pushing buttons. It's really in the artist's deep, almost intuitive understanding of how light falls, how materials deform, how gravity acts, in the real world. That fundamental grasp of physics and perception is the secret ingredient, I think, that makes a digital object feel truly tangible.
So it's less about technical wizardry and more about seeing the world with an artist's eye than translating that observation into the digital realm. That's a fascinating way to put it. It sort of flips the expectation.
Exactly.
What are the different ways artists go about this modeling process then?
Well, our sources highlight three main types. First, there's direct modeling, which is a very straightforward method. You literally create and modify models directly on the screen, almost like digital sculpting, but often more geometric. It's excellent for beginners and perfect for fields like architecture and product design, which is why a tool like SketchUp, which we'll explore hands-on later, uses this approach.
That sounds incredibly intuitive, yeah. Especially for someone just starting out.
Then you have parametric modeling. This method is based on parameters and constraints. Think of it as a smart system where all parts of the model are interconnected. If you change one parameter, say the height of a component, It automatically updates and affects the entire model, maintaining its integrity.
Okay.
This is very powerful for designs that need to be easily adapted or iterated upon quickly.
So it's more about setting rules and relationships than just pushing and pulling shapes directly.
Precisely. And finally, there's sculpting. This is a more free-form method, very similar to shaping clay in the real world.
Like digital clay.
Exactly. You add and remove virtual material to create intricate details. This technique is particularly popular in the movie and game industry for character design, organic shapes, creatures. Software like ZBrush is a prime example. It's renowned for its highly detailed digital sculpting capabilities. You see it used for creating complex characters in major films all the time.
Okay, so after putting all that effort into crafting that intricate 3D model, the next challenge is making it truly look real, right? Giving it that lifelike quality. And that's where rendering comes in, I guess. It's where the magic of light and shadow transforms abstract data into stunning visuals.
That's absolutely right. Rendering is the process that transforms those abstract 3D models into high-quality, realistic images. It essentially simulates how light behaves in a real environment, which is, well, fundamental to how we see things.
And what are the key techniques used to achieve that stunning realism?
Well, one of the most powerful is ray tracing.
Ah, yes, I've heard a lot about that.
Yeah, this technique simulates how light rays actually travel in the real world, including complex behaviors like reflection, refraction, and even diffraction. The result is incredibly realistic images that capture the subtle interplay of light.
I remember when ray tracing started appearing more in games and films, it felt like a huge leap. What exactly was it about ray tracing that pushed visual fidelity so much? Was it just better reflections And what about shadows? They seem simple, but I guess they're crucial.
They absolutely are crucial. Shadows are essential for creating depth and realism. What's fascinating here is that our very ability to perceive 3D relationships in the real world is largely due to shadows.
Huh. I never thought of it that way.
Without them, objects would appear flat and, well, ungrounded. We distinguish between hard shadows, which have clear, sharp edges, typically used for direct light sources like sunlight,
Okay.
and soft shadows, which have blurrier edges used for diffused lighting, like from clouds or indoor light sources. Different shadows tell you different things about the light.
It's incredible how much our brains rely on something as subtle as a shadow. Does that mean designing convincing shadows is one of the hardest parts of rendering? What about reflections, then?
Reflections refer to an object's ability to bounce light. Reflection effects can map the colors and details of the surrounding environment onto an object's surface, making it look much more real.
Right.
We categorize them as specular reflection, which occurs when light is directly bounced back, creating a bright highlight, like you see on a mirror, and diffuse reflection, where light is scattered evenly on the object's surface, creating a soft, even glow.
It sounds like rendering is incredibly complex, then. What are the practical implications of all this simulation? I mean, beyond just waiting a long time for it to finish.
Well, the main implication is that rendering is a computationally intensive and time-consuming process. It often requires significant waiting periods and really powerful computing resources because the software is literally calculating billions of light rays and their interactions. It's a real test of patience and hardware.
Okay, so even after all that modeling and rendering, we still need to think about the touch and feel of objects. That's where materials and lighting come in, I imagine.
Indeed. Materials describe the properties of an object's surface, things like its color, texture, and reflectivity. For example, a wooden material isn't just a brown color. It includes a wood grain texture and a specific reflectivity to simulate the wood's natural luster and how light would realistically interact with it.
And then there's lighting, which must be just as crucial for bringing a scene to life, right?
Oh, yes. Lighting simulates real-world light sources, affecting the color, brightness, and shadows of objects. And this raises an important question. How do light sources interact not just with individual objects, but with the entire scene?
Right.
A strong light source, for instance, creates distinct shadows and bright highlights on surfaces while also bouncing light around the overall environment. This connection reveals that 3D design is deeply rooted in the principles of physics.
So it's not just about making things look pretty. It's about simulating real-world physical properties, almost down to the, Well, not atomic level, but pretty detailed.
Pretty much, yeah.
What are some of the advanced concepts in this area that truly elevate realism?
Well, advanced concepts include understanding textures, which are images applied to surfaces to enhance detail, and roughness, which controls the coarse or fine detail of a surface, influencing how light scatters.
Okay.
Then there's reflection and refraction, simulating how light reflects off or passes through materials like metal or glass. This requires complex calculations of material properties. And light models control how light interacts with object surfaces, influencing brightness and hue.
Gotcha.
Our sources gave a great example, creating a realistic wooden table model. It requires a brown color texture, sure, but also a wood grain texture for detail, appropriate reflectivity for its natural gloss, and carefully placed light sources to simulate indoor lighting and create realistic variations in light and shadow. It's all about making it feel real and tangible.
Okay, so once you've got your beautiful rendered models, the next step is bringing them to life through animation. This is where static 3D models start to move, creating dynamic, lively scenes.
Right. And one of the core techniques here is keyframe animation.
Keyframes.
This method involves setting a model's position or state at specific times. These are called keyframes. The computer then calculates the movement between these points, creating smooth transitions.
It sounds like keyframe animation offers a really precise level of control. How does that compare to, say, some of the newer AI-generated animation techniques? Are there times when you simply need that granular, frame-by-frame control, maybe for a very specific facial expression or a subtle movement?
That's a great question. Keyframes provide that absolute customized control over animation, which is often crucial for artistic intent and nuanced performances, especially when AI generation might not always produce the exact desired movement or expression you're looking for.
Makes sense.
Another vital technique is path animation. This allows a model to move along a predefined path. It's often used for complex movements like an airplane following a specific flight route, with its angle changing accordingly, or even orbital movements of satellites.
And when you're animating, you're essentially directing a miniature film, aren't you?
Hmm.
How do camera angles and movements play into the storytelling? Is it as crucial in 3D as it is in traditional filmmaking?
Oh, it's absolutely crucial for storytelling. Adjusting the position, angle, and focus of the camera is vital to guide the viewer's gaze, enhance visual effects, and increase storytelling tension in 3D animations. Wide-angle lenses create broad views, while long-focus lenses bring far objects closer for close-up shots. A well-designed camera movement is truly vital for effective 3D storytelling, just like in filmmaking. It controls how you experience the scene.
So we've covered the basics, but 3D design is constantly pushing boundaries. What are some of the advanced techniques that really elevate a 3D creation to the next level?
There are several powerful methods. First, subdivision is a technique used to increase the detail of a model without making the underlying geometry too complex.
How does that work?
Well, it adds more details to the basic geometric shapes, making the surface smoother and more refined. Think of transforming a simple block into a more rounded, sphere-like shape with just a few clicks, instead of adding tons of points manually.
That makes a lot of sense, adding detail without manually creating millions of tiny polygons.
What about bringing in real-world physics? That must be complex.
That's physical dynamics. This simulates real-world physics rules, like gravity, friction, collisions, making the behavior of 3D models closer to real-world objects. This involves understanding Newton's laws and material properties like mass, elasticity, friction. For instance, simulating a ball rolling down a path realistically affected by friction rather than just moving along a predefined curve.
That's where the detail really comes alive. And then there are things like fire, smoke, hair. Those must be incredibly complex to simulate accurately. They are, and for that, we use particle systems. These are powerful tools for simulating various natural and man-made phenomena: fire, smoke, hair, snow, rain, sparks, you name it.
Okay.
These systems consist of numerous small, independent particles, each with its own attributes: location, speed, lifespan, color, size. For example, creating the effect of fire involves simulating a group of particles moving upwards, gradually disappearing, and changing color from yellow to red. Tools like the Unity Particle Pack exemplify these capabilities, offering pre-made, customizable effects that can save immense amounts of time.
So you don't have to build every single wisp of smoke or strand of hair individually. Phew, that's a huge efficiency gain.
Significantly.
What about other types of simulations beyond individual particles? like cloth.
Right, beyond individual particles, simulation plugins are essential tools. They expand 3D software features, mimicking complex physical phenomena like the softness and realistic movement of cloth, the flow and flutter of hair, and the dynamic behavior of fluids like water, smoke, or fire. They apply real physics laws directly to the material itself.
Given how much detail and complexity goes into 3D, is there a way to automate some of the more tedious tasks, like making a whole forest?
Absolutely. Script automation. Using scripts to automate repetitive tasks is crucial for efficiency. Imagine creating millions of leaves on a tree or thousands of soldiers in a battlefield. Manually doing that would be practically impossible.
Yeah, no kidding.
Scripting allows for automatic generation and even setting keyframes for large-scale animations.
And finally, enhancing the final look. Are there extra tools for rendering?
Yes, that's where rendering plugins come in. They enhance 3D software with dynamic features like vivid color palettes and even more realistic lighting effects, further pushing the boundaries of realism beyond what the core rendering engine might offer out of the box.
Okay, we've covered a lot of theory and high-end techniques, but now let's ground this with a hands-on exploration using SketchUp. You mentioned it earlier, it sounds like a fantastic stepping stone into 3D design for anyone.
SketchUp is quite accessible, yeah. Especially its web version, which you can find at https://my.sketchup.com. It's best viewed in Chrome, usually.
Okay.
And it allows users to save models directly to the cloud. You need a Trimble Connect account. That's their cloud storage system. Google Sign-In is highly recommended, just makes it easy.
Right.
It's renowned for its intuitive interface and direct modeling approach, making it an excellent choice for beginners and pros, particularly in architecture and product design.
I remember SketchUp being part of Google at one point, which is pretty cool. What's its history and what features does it offer now? Is the free version still useful?
You're right, it's had a varied history. Was part of Google, and now it's a Trimble product. While the free web version's features are gradually being reduced, for instance, direct video export and including materials when you export the model are no longer available, it still remains a really powerful tool for learning and basic projects.
Okay.
The Pro version, of course, offers more extensive features, including something called SketchUp Diffusion, which integrates AI for generating finished images directly from your scenes.
Interesting. So it's a great entry point. Let's talk about basic navigation in the interface. How do we move around in this 3D space? What are those core controls?
Okay, the core mouse controls are fundamental for navigating. You left-click to select objects. Pretty standard.
Yep.
To zoom, you scroll the middle mouse wheel. For orbiting around your model, basically rotating your view around it, you click and drag with the middle mouse button pressed down.
Orbiting, got it.
To pan across the scene, sliding your view side to side or up and down, you hold Shift and then click and drag with the middle mouse button.
Okay, Shift plus middle mouse.
And a quick tip, double-clicking the middle mouse button will recenter your view on everything in the scene. Very handy if you get lost.
That's super helpful. What about those essential keyboard shortcuts, the tools you'll be using constantly?
Right, shortcuts save a ton of time. For drawing, L is for line, R for rectangle, and C for circle.
LRC, easy enough.
P is for push-pull. This one is absolutely crucial. It's how you take flat shapes and extrude them into 3D forms.
The core 3D tool, basically.
Pretty much. M is for move. T for tape measure, incredibly important for precise measurements and creating temporary guidelines. And E for eraser.
MTE.
Oh, okay.
Precision is absolutely key in design, so how do we handle units and making sure everything lines up perfectly?
Good question. It's vital to set your model's length units first, like meters or centimeters or feet and inches, and also the display precision, like down to 1 or 2 decimal places. You can also set a snapping distance, like maybe 0.1 meters, so your cursor kind of jumps to increments on a grid.
Snapping helps a lot.
Yeah.
And when you're drawing, how do you make sure your lines are straight and aligned correctly, avoiding those slightly off wonky angles?
That's where guided drawing comes in. You'll rely heavily on SketchUp's automatic inference point.
Inference points.
Yeah, little visual cues, like it shows you endpoints, midpoints, and edge highlights appear as blue, red, or green lines when you're drawing parallel to the main axis.
Okay.
These cues tell you when you're aligned perfectly to an axis or snapping to another point. You learn to trust them.
Okay, so enough high-level theory for a bit. Let's ground this with some hands-on examples. We'll walk through some practical things you actually learned to create with SketchUp, starting really simple. How would you go about making a basic cube, for instance?
Right, you saw how straightforward it is. To create a simple cube, say 2 meters by 2 meters by 2 meters, you first draw a rectangle on the ground plane.
Using the rectangle tool.
Exactly. The key is to click once to start, release the mouse button, move the mouse to show the direction, then type your desired dimensions for a 2x2 rectangle. You just type 2x2 and press enter.
Click, move, type, enter. Got it.
Then you use the push-pull tool, P, click once on that flat rectangle face, release, move the mouse upwards to indicate height, and type 2 for a 2-meter height, then press enter again, boom, cube.
That really is intuitive. Okay, what about something slightly more complex, like a simple chair?
For that, you'd start using the tape measure tool, T more. You create precise guide points, maybe at 0.5-meter increments, to mark out where the legs and seats should be.
So the guides act like temporary pencil marks.
Exactly. Then you draw lines, L, along those guides, and use push-pull P again to form the chair's shape, pulling out sections for legs and maybe a backrest. It's kind of like building with virtual blocks, guided by your measurements.
And the house model. That seemed like a bigger jump.
Not as big as you'd think, structurally. You learn to create a basic house by starting with, say, a 10-meter by 10-meter base rectangle, then push it up P to maybe 10 meters height.
Okay, a tall box.
Then, for the roof, you'd find the midpoint of the top face's edge using the line tool, L, draw a line across the center, then grab the move tool, M, click on that center line and pull it straight up, maybe 3 meters. SketchUp automatically creates the pitched roof surfaces.
Wow, clever.
And yeah, you also created windows and a garage door using rectangles R and push-pull P to make indentations or cutouts, and applied semi-transparent materials for the glass.
A pool seems even more detailed, especially with curves and depth.
For the simple pool, you drew maybe a 10-meter by 5-meter base rectangle. Then, to add curved ends, you use the 2-point arc tool. Click 2 points, then pull the curve out maybe 2 meters to define the pool's outer shape.
Okay, arcs for curves.
Then you used push-pull P to raise the pool edges, say 0.5 meters. Then the offset tool was handy. You select the top face of the pool edge, use offset to draw a smaller, identical shape inside it, representing the water area.
Ah, offset creates like an inner border.
Exactly. Then you push that inner water area down slightly, maybe 0.1 meters, to give it that realistic depth.
And bringing them to life visually involves adding materials, right? Making it look like water or glass.
Yes, exactly. You applied materials like water using transparent water textures, which often have a little diagonal line on their icon in the library to show transparency and transparent glass to your models. That brings them to life visually and lets you see through them, making them feel more complete.
You also explored importing ready-made 3D objects. That must save a lot of time compared to building, say, a detailed car from scratch.
Oh, it's a huge time saver. You imported ready-made 3D models from SketchUp's 3D warehouse, like a car model.
The warehouse, right?
Then you use the scale tool, S, to adjust its size to fit your scene, and the rotate tool, Q, to position it precisely. Though rotating can be a bit tricky sometimes, you have to be careful where you place the rotation gizmo to get the axis right.
Yeah, rotation can be fiddly. And for a taste of animation, you even learned how to animate scenes, even in the free version, kind of.
Yes, by setting up multiple camera views in the Scenes panel, each scene saves a camera angle.
Ah, like saving viewpoints.
Exactly. Then, playing through the save scenes creates a fluid camera movement, like a simple fly-through. While direct video export isn't available in the free version anymore, you learned you can just screen record your animation, maybe using Windows 11's built-in screen recording feature, to share your creations as an MP4 file.
Clever workaround. Finally, experimenting with different visual styles and shadows.
Yeah, you experimented with various visual styles from the Styles panel, like making it look like a pencil sketch or a wireframe model, which is cool because those line drawings can sometimes be fed into AI art tools for creative effects.
Oh, interesting connection there.
And you also touched upon how SketchUp can simulate shadows based on time of day and year, which connects right back to what we discussed earlier about the importance of light and shadow in realistic rendering. Even if the dynamic shadows aren't always perfectly rendered in the free version's scene playback animation.
Right, it all connects. So what does this all mean for you, the listener? We've taken a deep dive into the fascinating world of 3D media. We started by exploring the surprisingly high costs and complex techniques involved in professional 3D design, then moved through the core concepts: modeling, rendering, materials, lighting, animation, right down to advanced physics simulations like particle systems and fluid dynamics.
And then we grounded all of this with practical hands-on experience in SketchUp. You saw how to build everything from a simple house and a pool to even your own 3D name.
Yeah. Understanding these foundational principles of 3D design is incredibly empowering, isn't it?
It really is. While AI tools are becoming increasingly capable and can generate stunning content quickly, mastering these basics allows you to move beyond simply accepting what AI generates. You gain the ability to customize, refine, and truly objectify your creations.
And objectify is a key term here, I think. If something isn't properly objectified in 3D, meaning it's a distinct, manipulable geometric entity with defined properties,
Hmm.
it's incredibly difficult to make precise adjustments or integrate it seamlessly into a larger scene.
Exactly.
This deep dive has shown you how these core principles are not just theoretical, but immediately applicable for true creative and commercial applications.
And as 3D technology continues to evolve, especially with advancements in AI-generated content, the possibilities for creating immersive, dynamic, and visually stunning experiences are truly, well, limitless.
So consider this provocative thought. How might your newfound understanding of 3D modeling and animation transform the way you visualize, interact with, and even perceive the digital world around you? Think about how understanding physical phenomena like light, shadow, material properties directly translates into building believable digital environments. It really changes how you look at what's possible in the virtual space, doesn't it?